Okay, we're going to kind of switch gears a little bit. We are going to look at dividing up data sets now. And if you ever had to take any standardized tests, you have probably seen percentiles. Because when they do standardized testing, they tell you what percentile you fell in. And basically what that means is your data set is divided into hundreds, with percent meaning hundreds. If you were in the 55th percentile, that means you did better than 55% of the people who took this particular test. If you were in the 35th percentile, you did 35% or did better than 35% of the other people that took this test. So percentiles is common, especially with standardized testing. Now deciles, they follow the same idea, but instead of being divided into hundredths, they're divided into tenths. So you have to kind of visualize how this is going to work. If you are in the third decile, that would be equivalent to the 30th percentile, because deciles are based off of tenths, where percentiles are based off of hundredths. So your third decile would mean you did better than 3/10, which is also 30 percentiles of the data. Not used quite as often as percentiles. Now the one we're really going to focus on is the quartiles, and this is divided into fourths. So if you have a data set and you divide it up into fourths, you're actually talking in terms of 25%. So this one right here would be like the 25th percentile. Here you would have your median, or your 50th percentile, and then your 75th percentile. So we're going to use the quartiles most. And our first quartile breaks up our data into the bottom 25 and the top 75. So that first quartile, when you cut that data right there, you have the bottom quarter and then you have the top 3 quarters. And one way to think about this is it is the median of the part of the data set that lies at or below the median of the entire data set. Now, if you dissect this sentence here, and we start at the end, we need to find the data set that lies at or below the median of the entire set. So if I split my data right down here, right at the median, I'm talking about this half of the data, and my first quartile is the median of this lower half of the data. That's what that sentence is saying. Okay, our second quartile is just the median. It splits our data into the bottom half and into the top half. And now the third quartile, that splits our data right here, and that splits it into the bottom 75% and the top 25%. So this would be the median of the part of the data that lies at or above the median of the entire set. So it's the median of the top half of our data set. We're going to be using the quartiles quite a bit in these next few sections. Now, with regards to quartiles, we will often need to find the interquartile range, which you'll have referred to as the IQR. And what it is it's the difference between the first and the third quartiles. So our interquartile range is quartile 3 minus quartile 1. We're going to end up using this number in a calculation. We are also going to look at the 5-number summary. And our 5-number summary is a set of 5 numbers, and it's the minimum and quartile 1, quartile 2 or the median, quartile 3, and then our max. So if we're talking about the interquartile range, it's the difference between quartile 3 and quartile 1. Basically what it tells us is it'll tell us how long this line is here. From quartile 3 to quartile 1, how far apart are they? Now, with our 5-number summary, we are also going to have to consider what's called an outlier. And this is an observation that falls well outside the overall pattern of the data. If we think about that 3 standard deviation rule, if this is the top of ours and this is the bottom of ours. An outlier is going to be somewhere out here or somewhere down here. It's going to be one of those values that doesn't fall within our 3 standard deviation rules, but just because it doesn't fall within doesn't make it an outlier. There are some other things that have to be considered. One of the things we can do is we can use that interquartile range to help us identify potential outliers. This still isn't set in stone. But what we can do is if we have our interquartile range here, we can get kind of a general idea of, well, how far beyond our interquartile range should we be, or is it possibly an outlier? And from our lower quartile, we subtract 1.5 interquartile ranges. So let's say that our interquartile range is 10. Well, and my lower cutoff point here is 50. My quartile 1 is at 50. If my interquartile range is 10 and I want to know, how far back here am I probably not going to be dealing with an outlier, or if I get beyond that I probably have an outlier, well, I need to take 1.5 times my interquartile range, so 1.5 times this 10 would be 15, and I'm going to subtract that from my 50. So down here at 35 is where I would be concerned. If I start getting data values that are past this 35, probably going to be an outlier. Still doesn't make it an outlier for sure, but it's potentially going to be an outlier. So since my interquartile range is 10 and I had my quartile 1 be 50, that means my upper cutoff here has to be 60 for quartile 3. And if I go up looking above this, I'm still going to have the same thing. I'm going to add, though, 1.5 of my interquartiles to this quartile 3. So I would be adding 15, and I would be interested in 75. So if I get beyond 75, there's a good chance that I have an outlier. Doesn't make it an outlier for sure, but it kind of gives us that red flag that we need to be doing some more looking. Okay, now this 5-number summary can be displayed with a box plot. And what a box plot is it's just a visual representation of our 5-number summary. We draw it over top of a number line. That way we can see where our values actually line up. So we would have our number line going across the bottom. And then we would graph our minimum, whatever our minimum value is down here. We would have quartile 1 is going to be the beginning of a box. Quartile 2 is going to be somewhere inside the box. Now, it doesn't have to be right in the center of the box. It can be farther to the left, farther to the right, but it'll be somewhere inside the box. Quartile 3 is the end of the box, and then our maximum value is up top here. So when you're drawing a box and whisker graph, you need to find your values, and you can just plot them with dots first, and then you can from there fill in the box part of it, in the box plot part. Now with box plots, if there is a potential outlier, and that's by using the interquartile range, the next adjacent value would become the minimum or the maximum, and the outlier would be represented by an asterisk. So let's say that this value right here was 30, and my cutoff was at 35 for potential outliers. Well, if I have to kick 30 out of my group, instead of putting it as the end of my box plot, it is going to become an asterisk, and my next lowest value, so let's say my next lowest value was 38, that will become the new end of my box plot. So if there is an outlier, it'll be represented by, or a potential outlier, it'll be represented by an asterisk, and then I just kind of kick that one out of my set, and I go to my next lowest value for my minimum. Now with all this information we've gotten, we're going to start looking at, well, what if I'm dealing with the population instead of a sample? We've primarily been talking about samples. Now we're going to look at populations. And when we're talking about populations, we're talking about parameters, not statistics anymore. A parameter is a descriptive measure for a population, whereas a statistic is a descriptive measure for a sample. Easiest way to keep them straight is a population starts with P, parameter starts with P, sample starts with S, statistic starts with S. So they're really the same idea, just applied to two different situations. And since we do have two different things going on here, we do have different equations. When we have a population mean, we use the Greek letter mu, which is this goofy looking U here. So if we're talking about the population mean, we are now talking about mu. But notice that the equation is almost identical. We still have sigma, we still have x sub I. Now though, we're dividing by a capital N instead of a lowercase n. The difference would be with our sample, we divided by a lowercase n, and then our notation for the mean was x bar instead of mu. Okay, here is our standard deviation. This is the population standard deviation. Almost the identical formula, except for, again, we have mu in place of our x bar, and a capital N again, and then this Greek letter right here is lowercase sigma. So it's still the exact same process, just slightly different. And also, with our sample standard deviation, we divide by n minus 1. Well, when we have a population, we just divide by n. So it's still the same process, just slightly different variables that are used.